I'm going to be presenting on behalf of my colleagues, and particularly Thomas Hearon from EOG and Mary Carr from the School of Mines, but most importantly, of course, the people who've done the bulk of the work for this particular project, and that would be the students. So Wes, basically in the field area near Aspen, Colorado, Savannah over here on the right near Walcott, Colorado, and then Haley down towards the base in here. So those are the people who've done the bulk of the work, and I'm going to be sharing some preliminary results today. But as ever with most projects, we build on the people who've worked before us, and this project is no exception to that. And I think it's particularly appropriate in terms of standing on the shoulders of giants that we've really built on some of the work that Ogden Tweeto did, who was named Scientist of the Year by RMAG in 1978. And a paper that Tweeto published in 1977 on the tectonic history of west central Colorado contains the following quote, that thick upper Paleozoic sediments in the trough between the uplifts consist in part of an evaporite facies. Flowage in areas of thick evaporites began as early as late Permian time and strongly affected Permian and Triassic sedimentation as well as later structure. So clearly to me in this landmark paper, Tweeto clearly recognized this phase of long-lived salt tectonics in the Eagle Basin prior to the Laramide orogeny, but by and large, these observations were ignored for about 40 years. So before we get into talking about the Eagle Basin specifically, I thought it might be just relevant just to give a very brief overview of where we are in terms of our understanding of modern salt tectonics. And if we go back into the early part of the last century, really up until probably the mid-1980s, many people viewed salt structures as developing, particularly salt diapirs, primarily due to the low density of salt compared to other sediments. So in the graph over here on the left-hand side, this is a common graph at the time showing how, as you basically come down with depth in these sediments from the Gulf of Mexico, coming down to about 5,000 meters, so about 18,000 feet. But so you can see that the generally terrigenous sediments increase in density as they become more compacted. But if you take salt, and by salt I'm talking primarily about halite, it starts off with a density of 2,200 kilograms per meter cubed at the surface and decreases slightly. And then there's a crossover point at about 1,500 meters burial depth where it seems that the salt will be less dense than the surrounding sediments, which is true. Over on the right-hand side, this is just a cartoon of one of the experiments by Nettleton in 1934, where he modeled salt and the overburden as viscous fluids, with the salt modeled as crude oil, so relatively light or less dense, and then corn syrup as being the denser overburden. And this produces a classic Raleigh-Taylor instability, and we generate a diaper of the crude oil, which moves up through the overburden or the fluid. The problem with these sorts of models is that the overburden is, however, hardly ever viscous. In fact, it's generally strong, brittle, and stiff, which means salt buoyancy is unlikely to trigger diaperism. So we can kind of do that in terms of the buoyancy being a primary driver of salt diaperism. It can be important in certain situations, but we don't think it's the primary driver. So if that's not driving salt diaperism, what is? Well, what we know extensively from the modeling work done by people at the Applied Geodynamics Lab at the Bureau of Economic Geology, and one of their early models is now running on a loop in the screen, is that we can actually view salt tectonics and particularly salt diaperism as primarily driven by differential loading. So on the left-hand side, we have three types of salt diaperism. We have reactive salt diaperism, which is where extension creates room, which is what's happening over here on the right-hand side. So as we thin the overburden through extension, we have the rise of the salt as these triangular salt diapers. In the middle, we have active diaperism, and that's when the salt actually creates room. So we thin the overburden, and we're just going to do that now in the model, to a point where it's thin enough the salt can break through that roof. Once the salt reaches the surface, we then shift into what we call passive diaperism, where the salt is up at the surface and the sediments downbuild into the mini basins, as we call them, on either side. So let me move forward, because that doesn't occur in this particular movie, and show you then a model, again, from AGL of a salt diaper, now in red in the center. So you can see this large salt structure outlined in the center. We have two salt pillows over on the flanks on either side, and then between those we have these two dots represent where we have salt wells, where the salt at that basal level has been completely evacuated. And what I'm going to show you shortly is basically a cartoon restoration of this structure. In other words, how it evolved through time. And again, this, what you'll see is the primary mechanism of diaperism is passive diaperism, which is defined as ongoing near-surface syn-depositional growth of a diaper by Rowan and Giles. And you can see the more extensive definition here. But the key thing is the salt is going to stay at or close to the surface throughout. And the sediments in the mini basins on the flanks, so we call these deep, relatively small area basins associated with salt withdrawal mini basins. So this is a mini basin from basically the top of the green down to the base of the blue. And the other thing you'll see is through time, the mini basin thicks shift. So in the dark blue, they're down here, and gradually they shift over to be adjacent to the salt diaper. And that's actually tracking the evolution of the structure. So in this cartoon, I've basically drawn a line on here just to fix the surface. So we've got a point that's basically not moving. And now I'm going to show you the restoration phases of that previous diaper image, but we're going to go forward through time. So at the point where we're depositing that dark blue layer, you can see we have this extensive, wide salt diaper up at the surface. We have the mini basin in the dark blue developed on either side, and then we have these salt pillow structures sitting off towards the flanks. If we start to evolve this through time, you see that the diaper is growing in height, it's getting narrower, but it's not basically moving above this surface. We're creating height on the diaper by basically an overall substance, so the base of the salt is moving downwards, but also by the sediments thickening into the areas where the salt is being withdrawn. So you see the pale blue over on the right-hand side is thickest above this area where the salt is now actually welded out. And as we move this forward through time, we still keep growing the salt diaper. So this passive salt diaper is getting taller through time. At the start of or during the dark green, it actually starts to flare out slightly, and that's because the rate of salt rise is exceeding the rate of sediment aggradation. If we move it forward to the pale green phase, you can see that flaring is now even more dramatic, and we're actually seeing a quite substantial increase in the salt rise rate as the diaper flares out. Ultimately, though, the fact that we've welded out the salt at this source layer means that the diaper is not going to be able to keep growing indefinitely. And once we're no longer able to bring salt into the system, and remember we'd be dissolving salt probably from the top of the system quite extensively, we end up burying that salt structure with the pale brown layer in here. So this is how we think many salt structures evolve, and they can grow over considerable periods of time. Tens of millions of years is not unreasonable at all for some of these passive salt diapers. Okay, so let me move on a little bit then and talk a little bit more about mini basins. So again, salt mini basins are these deeper centers adjacent to one or more of these diapers or other salt-related structures where we generate accommodation by subsidence into the underlying salt. Now, mini basins can be quite complicated. They can contain these halokinetic unconformities that define sequences and successions at different scales. And this terminology is now quite complex, but just to point out that we can define, so the green box over here is defining what we call a megaflap, which is this draping unit which starts off at the base of the mini basin and then drapes for several kilometers up the flank of the passive salt diaper. In red, we can then talk about mini-basin tectonostratigraphic successions, which are large-scale packages within the mini-basin itself, which can show different shapes and also have significant unconformities. And then in blue at the top of here, we can also talk about composite halokinetic sequences. And those develop right on the edge of the roof of the salt diaper, where we have drape folding on the flank as we move from the roof of the salt diaper into the mini basin. So those are very specific to developing right on the edge of an evolving passive salt diaper. And just to give you some idea of scale, okay, these structures can get really large. This is a seismic profile from the Gulf of Mexico. We're in thousands of feet on the right-hand side, so we're going down to about 43,000 feet, 13,000 meters or 13 kilometers. So the salt diaper over here in the center, if you measure from top to base, it's about 10 kilometers tall or 33,000 feet. And if you look at the thickness of the mini basin sediments, they're on the order of about 40,000 feet of sediments. So we can generate very tall salt diaperic structures growing primarily through passive diaperism. We also know a little bit about what happens to salt structures when we shorten them. And again, a lot of that work has come from modeling analog models. So over on the left-hand side, you've got a salt diaper in here in black, which is being shortened in this analog model with the sandbox layers above. You can see how we can weld off or close off that salt feeder during shortening. We can then actually have thrusting where part of the system is reactivated, and then we also have another thrust. And the block diagram on the right shows, again, some of the superficial structures as well as the pinched off and shortened salt diapers that we might expect. We know we're dealing with shortening because we're in an area that was substantially affected by the Laramide orogeny. You can see this large regional map from Yonke and Wheel from 2015. So the Eagle Basin is approximately this area outlined in the red circle. And then the green line is the cross-section over the right-hand side, which is some work which I know is ongoing with Ned Stern and his colleagues looking at this transect along I-70 and then restoring the Laramide shortening across that transect. And you can see the Eagle Basin sits kind of in the middle of this profile, and they're interpreting approximately 50 miles of translation. So we do have a significant amount of shortening across this system. Okay, so with that brief review, let me move on to talk about the Eagle Basin. So for most of us, it's sitting due west of where we are now. So obviously Denver in the Front Range. We cross over the Front Range uplift, and the Eagle Basin basically starts approximately at Vail Pass, extends down to south of Aspen, over towards Glenwood Springs, and then the northwestern tip will be up towards Meeker. So it's a pretty large basin, okay? And I've also included or highlighted the Paradox Basin in here down in southwest Colorado, because many of you probably know that basin contains salt structures that have been extensively studied. So we can use those as a potential analog when we're trying to unravel the more complexly deformed salt walls and salt diapers in the Eagle Basin. So let me show you kind of a regional setting. If we go back to approximately 307 million years ago, so during the late Carboniferous, the paleogeography from one of Ron Blakey's beautiful reconstructions in here outlines the Paradox Basin down in southeast Utah and southwest Colorado. And this would be at a global sea level low stand. So the basin is isolated from open marine conditions, and it's basically depositing evaporites, an evaporite system comprised of cycles. We see the Uncompahgre uplift towards the north, this ancestral Rocky Mountain uplift, which bounds the northeast flank of the Paradox Basin. And we think that then, as we move further towards the northeast at the time in here, we have the Eagle Evaporite Basin, which you can see is similar in scale, if not slightly larger than the Paradox Evaporite Basin. And that sits between the Front Range uplift to the northeast and then bounded to the southwest by the Uncompahgre. The interpretation is that these are flexural fallen basins, so the subsidence and accommodation is generated by the uplift of these basement cored mountain ranges. The evaporites are then being deposited basically during glacial-eustatic low stands, because at this time, at the end of the Carboniferous, we have these large glacial-eustatic cycles because we have greenhouse Earth with icehouse Earth with ice at both the poles. So we'd expect to see these large fluctuations. So we think those systems are pretty similar. If I simplify that diagram a little bit and just focus now over towards the paradox basin, again, the salt walls have this linear structure over in the paradox, northwest to southeast striking in general. And I'm just going to show you three cross sections, A to A prime, B to B prime, and C to C prime, which transect some of those salt wall structures. So the two at the top are based after work by Helmut Doling. And again, these are all one-to-one cross sections. So if you focus on A to A prime at the top, this is the Salt Valley salt wall, which is the largest salt structure in the Utah part of the Paradox Basin. It's approximately 4.5 kilometers tall, so around 15,000 feet, and about 6 kilometers wide or so. You can see the extensive mini basin thicks developed on the flank above the welded salt on either side of this particular structure. So again, we're seeing a long phase of passive salt diaprism associated with the growth of this. We come down across section B to B prime through Moab, Valley Salt Wall, Castle Valley, and the Fisher Valley structure, seeing similar geometries. The structures are a little shorter, but again, we're seeing these large mini basin sequences on the flanks of the salt wall. We crossed over into Colorado. So basically this cross section from Escosa et al. Basically what we've done now is change the color of the salt. So the salt's now in pink, and we're coming across Gypsum Valley and Paradox Valley salt walls. But again, you can see this extensive thickness of mini basin sediments deposited on either side above these welded areas on the basal salt layer. So we think we have some pretty good analogs in an area which doesn't seem to have been significantly shortened during the Laramide orogeny. So let's move on onto the Eagle Evaporite Basin. And what we're going to do is focus in into this area, this box in here, which is really the area of the Leadville quadrangle map produced by Tweeter et al. So covering this extensive area. And again, we use that extensively for building some of our own maps. So if we zoom into that area, I'll show this map a number of times. And after this slide, I'll actually break it down into its components. So what we've tried to do in here is incorporate a lot of different published data to establish the position of the basement chord uplifts and the fault structures as where we have salt up at the surface and interpreted salt walls and salt welds, and then also the mini basin structures, which are colored according to what we currently think is the primary age of mini basin development. So from dominantly Maroon age, Pennsylvania to Permian in red, Maroon and State Bridge age, Permo-Triassic in orange, and then dominantly State Bridge or Triassic in yellow. So let me break down this map somewhat into its components. If we strip off most of the layers and just come back to the distribution of the Eagle Valley Evaporite, or the present-day salt, you can see there's an extensive amount of salt up at the surface in the northern part of the basin through here. We come down into the south around Aspen. We have these linear salt walls, which are then connected in places by interpreted salt welds. Some of those are highly speculative based on our current work up to this point. We can mark off the approximate extent of the evaporite deposition. This is coming from the work of people like Mallory in 1970, over towards the northeast and then off towards the southwest, and then the ancestral Uncompahgre uplift down towards the southwest, and the ancestral front range towards the north. So we see a lot of salt up at the surface. We have one key well, which is a data point which basically drilled through the Eagle Valley Evaporite in the subsurface, and suffice to say at this point it contained a number of halite beds within the evaporite cycles. I'll come back and talk about this shortly in a bit more detail, but that is a key data point in terms of giving us some subsurface information on the salt. Okay, if we move forward then and overprint the Laramide shortening structures, which are in red, along with the basement chord uplifts, which are in gray, you can see how the basin is then dissected by these structures. We have the White River uplift, the Laramide age basement chord uplift sitting up in the northwest part of the basin, and we've actually stripped off a substantial part of the salt and mini basin sequences over this particular structure. We move down towards the south and east. We have the Swatch uplift, which is Laramide partly in age, but also some of that uplift is related to these large extensional faults of Neogene age in blue as well. So we have two later structural events in the eastern part of this particular map. We also then have the Elk Range thrust, which basically runs along the southern edge of the salt basin, and I think it's intimately related to the edge of the salt in terms of the development of that structure. And as you move along strike, you can see how that transfers into the Grand Hogback monocline, Laramide age monoclinal fold structure, which again seems to track relatively closely to the edge of the salt. So again, there may be a relationship there as well. In the northeastern part of the map, you can see now we're overprinting the Front Range Laramide uplift and the Gore Range uplift on top of that previous ancestral Front Range. So we have a strongly dissected and shortened salt basin that we're trying to interpret. Finally, then I'll just go back and show you the whole map again with the mini basins, and just to, again, emphasize that these are our current interpretations. They're evolving literally all the time in terms of what we think is the dominant age of the mini basin sequences within these different mini basins. And you can see they're all named, and in general, it seems that the age of the dominant mini basin filling packages seems to get younger somewhat from southwest towards the northeast. But again, I'll circle back to that right at the end. Okay, so let's start to pick this apart in a little bit more detail. And first, we're going to go and look at the area that Wes worked on as part of his master's thesis at Mines. And this is located around Aspen and focuses on the Woody Creek mini basin up in here, and then to the south, the Snowmass mini basin. And then those are separated by this Woody Creek salt wall through here. So West was fortunate that he was able to use the USGS quadrangle maps. So this was from work primarily by Bruce Bryant and Val Freeman at the survey. And we were fortunate enough to be able to go in and work our way through their field slips and their field notebooks at the USGS library. And we gleaned a huge amount of information to build on from that. So that's the area that Wes covered in detail. On the left-hand side is showing a fairly simplified version of the stratigraphy. But in the deeper part of the section, in what we call the pre-salt, we have the Leadville, limestone, and Alder. Directly beneath the Eagle Valley evaporite, we have the Belden Formation. Then PE, this purple color, pale purple, is the Eagle evaporite. And then we go up through the post-salt section, and you can see that we're interpreting that salt tectonics lasted from approximately 300 million years ago, maybe a bit more, 310, all the way through to about 200 million years ago. So phase of salt tectonics that potentially lasted about 100 million years right through the Triassic. So let's focus in then on the work that Wes did in terms of putting this together. And what I'm going to show you first is just to give you an idea of the surficial outcrops that we see of these different units. So I'm just going to show you some of these. So the Eagle Valley evaporite crops out across the basin. In places, we have these gypsiferous breccia towers. There are a couple of people in here for scale. So these are in Monument Gulch, south of Aspen. We also, in places, see bedded evaporite overlain by the dissolved remnant of the Eagle evaporite, which would be the caprock. This is Thomas Hearon and myself sitting on that contact close to it. And again, we can see varieties of different bedded evaporites and gypsiferous breccias in these extensive surface outcrops. As I already mentioned, we do have one well in the Eagle Basin, the Champlain #1 Black Well, which basically logged a significant section through the evaporite, and the pale blue areas in here are distinctive as being halite from the particularly the low gamma ray signature. And we can compare those quite readily to wells from the Paradox Basin that again drilled through similar cycles of evaporite. And again, the work from Height and Buckner was hugely important in terms of defining these cycles within the evaporite sequences, basically showing a transgressive phase where we come in and finally deposit the black shale, which is the primary source rock in the Paradox Basin, and then the regressive phase where we increase salinity, ultimately depositing these thick halite beds at the end of each cycle. So again, just to emphasize, we think a similar process was happening during the deposition of the Eagle Valley evaporite. We jump up section to the maroon, again, probably very familiar to many people in the audience because we have the maroon bells in this view and Pyramid Peak. So late Pennsylvanian to Permian age sediments, we see a variety of different rock types. What I want just to stress in here is if we look across the Eagle Basin, we see a variation in thickness from less than 500 meters to over 4,500 meters in terms of how thick this particular formation can be. And we think a lot of that thickness variation is primarily due to salt tectonics. What's challenging in the maroon is basically, well, not only the fact that it often crops out in faces that look like this, so that makes it pretty challenging, but also actually correlating surfaces across different mini basins is quite difficult. We move up section then into the Permian and early Triassic. We have the State Bridge Formation, which for those of you more familiar with the Paradox Basin, this would be approximately Moenkopian age, something like that. We have reddish brown, interbedded, planar to ripple laminated siltstones, sandstones, and rare conglomerates. It looks quite similar to the maroon of outcrop, but we are able to define three distinct members. So we have the lower State Bridge, the Sloan Peak member, and the upper State Bridge. And that's really helpful in terms of being able to track the State Bridge formation across the basin. Again, it does show a very wide range in thickness from being totally absent to around 1,500 meters or 5,000 feet thick in some places. We jump up section again into the upper Triassic. We're into the Chinle Formation. Again, I'm sure very familiar to many of you. Upper Triassic in age, generally reddish brown siltstones and sandstones, but with a couple of distinctive units, the Garter conglomerate member and the mottled member towards the base. And again, these are useful correlation horizons. We do see a thickness variation, but you can see the range is getting less, and it seems during the Chinle, we're in that waning phase of passive salt diaparism, and by the time we get up to the Entrada Formation, overlying the Chinle, we see no evidence within the Entrada of any strong salt control on the distribution of that unit. Okay, so let's take a look at Wes's map. So this is basically the map that he produced from his field work, integrated with obviously the field maps and the published USGS maps from Bryant and Freeman for the 4 quadrangles. And what I'm going to do is just walk you through the kind of 6 characteristic features that Wes basically mapped out in here, which we think are primarily related to either salt diaparism or they're basically salt structures that are being shortened during the Laramide event. And then I'll highlight a couple of those just to show you the details. Again, this is the Woody Creek mini basin sitting over towards the northern side, and then the Snowmass mini basin sitting towards the left. And then the Woody Creek salt wall works its way up through kind of the center of the image and then heads off towards the northwest. So as I mentioned already, we do have these areas of evaporite outcrop up at the surface, and the interpretation is that where we have evaporite outcrop across the Castle Creek, sorry, I said Woody Creek, Castle Creek salt wall, it's connected by these vertical wells, okay? The other thing we see particularly in the Woody Creek mini basin is this vastly over-thickened maroon formation. So the total thickness of the maroon is in excess of 4,000 meters within this Woody Creek mini basin. It's significantly thinner when we drop over into the Snowmass mini basin towards the south. We also see abrupt thickness changes in the State Bridge. So again, as we cross the Castle Creek salt wall through here to the north, the State Bridge is approximately 730 meters thick. So a couple of thousand feet, only a short distance away, less than a mile, we're dealing with a state bridge, which is 150 meters thick, so about 500 feet. So those abrupt changes in thickness, we think, again, are characteristic of this fault-related evolution. We have areas of pre-Laramide unconformities where we can clearly demonstrate these major unconformities within the mini-basin sequences that clearly predate the Laramide orogeny. In the southern part of the basin, we have pre-Laramide growth faults. So normal faults generally dipping off towards the east, as you can see highlighted down in the southern part in here. And those show thickening within primarily the lower part of the state bridge. So again, it must be a pre-Laramide growth faulting we're looking at. And then finally, we have welds, or what we interpret as being these steep subvertical secondary wells are being reactivated as Laramide basement involved thrust faults. So let me just focus particularly on this area around the Castle Creek salt wall, where we have Eagle Valley outcrops up at the surface, and then particularly what happens when we start to look at the relationship between the Maroon Formation and the State Bridge Formation. So we're going to zoom into this red box in here. Again, this is from Wes's map that he produced from his own field mapping, and then again incorporating the data from the USGS quadrangle. So let me outline the area of the evaporite outcrops is kind of outlined by this black dashed line. We have an interpreted vertical secondary weld where we've closed off that vertical or subvertical salt wall, and then we come back into the PE as we head off towards the northwest part of the map. And if you look in the Woody Creek mini basin on the northeast side, this is where we see these interesting relationships. Up in the northeast part over here, you can see the dips are fairly low, and we seem to see pretty similar dips within the Maroon and the overlying state bridge. So the Maroon is in blue, the state bridge is in this purple violet color in here. What we see, though, as we move towards the salt wall structure, as we go through a syncline, and you'll see that the dips in the blue unit, the Maroon, steepen up very abruptly. So we go up to vertical at 90 degrees, and then along the edge of the salt, they're overturned at up to 52 degrees overturned right up against the salt. And this relationship extends all the way up the edge of the salt wall structure. If you look, though, in the overlying state bridge, you'll see the state bridge dips are all dipping back gently towards the north or northeast. So we have an unconformity between the underlying Maroon Formation and the overlying state bridge of around 40 to 70 degrees. But it's highly localized. It's only developed within maybe 1 kilometer to 2 kilometers at the most of the edge of the salt wall. By the time we move out here, we don't see that unconformable relationship. And again, that's a pre-Laramide unconformity. This is what it looks like if we basically go and have a look at some of the outcrops. You can see how steep some of these, the terrain is we have to work in. Here's some of the evaporite outcrop, basically down at the base of this image on the left-hand side. You've got kind of a sketch that Wes put together on the right-hand side. And if we come across the edge of the salt, we come into these very steeply dipping to overturned Maroon beds. And then in the background, this is basically the gently dipping state bridge with that unconformity projected out to produce that abrupt angular truncation of the steeply dipping to overturned Maroon up against the salt. And again, in the bottom right-hand corner, we have an analog from the Shivas Basin in Turkey, where again, we have these well-documented oversteepen beds up against the edge of the salt in basically the pale unit in here, and then these lower angle dips coming in and truncating those halokinetic folded units. So again, we'd interpret that these are drape folds. So we're drape folding coming off the roof of the salt diaper as we come into the mini basin and developing those really steep dips during the passive growth of the salt diaper during Maroon times. Show you a couple of cross sections, and again, Wes produced, as did Savannah, extensive cross sections through their field areas. So cross section A to A prime crosses this northern part of the Castle Creek salt wall, again, we were able to put together the cross sections using a variety of different data. So using Global Mapper was the primary tool in terms of integrating the data sources that we had. And then Wes and Savannah also put together restorations, so taking the present day geometry and restoring the cross sections back through time. I haven't got time to show you those restorations today, but again, we like to acknowledge both Blue Marble Geographics for Global Mapper software, and then Petroleum Experts for supplying us with the MOVE software. So let me show you cross-section A to A prime. And again, it highlights a couple of things. Here's the relatively narrow, steep-sided Castle Valley salt wall in the center in here. If we come into the Snowmass mini basin towards the south and west, you can see where we have a thickness of the lower state bridge of about 350 meters. We come across into the Woody Creek mini basin. We then have these steep to overturned dips within the maroon, these much lower angle dips within the lower part of the state bridge, and the state bridge thickness in here is around about 1,200 meters. So 3 to 4 times thicker than just on the south side. Moved along strike, and I'm going to show you a regional cross-section B to B prime, which Wes put together just south of Aspen. And that's crossing some of the growth fault sequences and then coming in towards what we interpret as this reactivated secondary weld, reactivated as a basement-involved Laramide thrust on the western flank of the Saguache uplift. So here's Wes's cross-section. So I'll start over here on the right-hand side. So here's the basement uplift. So this is the Saguache range with the basement and then the lower Paleozoic sequences basically forming a syncline sitting on top of that. The boundary through here then would be our secondary weld, which we interpret now as being a thrust or reactivated as a thrust with basement in the hang wall. We have very steep to overturn dips in the maroon and the lower part of the state bridge. And here I'll come back to those in a second. And then you can see this variation in thickness of the TRPSL. So the lower state bridge is significantly thicker here. It seems to then thin towards the west. But when we come up to one of these growth faults, you can see it's significantly thicker in the hang wall of this fault, which is dipping towards the east, than it is in the footwall, demonstrating a stage of growth within the lower part of the state bridge. We move over to this fault, and it seems that in this case, we're seeing actually thickening in the upper part of the state bridge in the chinley. On this growth fault, we move over to the western edge of the section, and I just want to note that now we have no state bridge. We have the chinley sitting directly on top of the maroon, so the state bridge has disappeared completely. If we extrapolate and our interpretations of this cross-section to depth, we can maybe come up with something like this. It would be highly speculative, below about plus 1,000 meters. But what we're interpreting is that these large growth faults would come down and detach potentially on these salt pillows down at the lower salt horizon. So this would be the depositional level of the Eagle Valley evaporites. So the normal faults are detaching on these salt pillows. We've got welded salt between the pillows, and as we come over towards the right-hand side, again, we've got another extensive area of welding and potentially a mega flap where the lower part of the maroon sequence, and again, you can see how thick the maroon is in here, it's basically close to 4,000 meters thick, would wrap up against what we'd interpret as being that original salt wall, which has now not only been welded shut, but that weld is reactivated as a secondary thrust weld. I mentioned that this is a key area in here where we see these very steep to overturn dips within the maroon and the state bridge, or the lower part of the state bridge. If we look at a cross section that Wes drew just along strike to the north, that's kind of important because it shows the relationship where we can see, again, overturned maroon formation at 82 degrees down the southwest or the left-hand corner of this slide down in here. And then we're projecting again this permo-Triassic angular unconformity, which is visible in the field. You can clearly see the dip change from overturned maroon to very gently dipping state bridge in here. So that's projected onto this cross section again, showing this clear pre-Laramide unconformity now at the base of the upper part of the State Bridge. Okay, so we've kind of covered that southern area, and I'm now going to just move up to the area that Savannah worked on for her thesis. So this is up in the northern part of the Eagle Basin, particularly around Hardscrabble Mountain. But we have, fortunately, a seismic profile which was basically run north-south pretty much across the Hardscrabble mini basin, just to the south of that black #1 well. And that's helpful because it gives us an idea of basically, the deeper part of the section and what's happening in the subsurface. So let me show you that seismic profile in here. So it's a 2D seismic profile based on, this is from Scott et al. In 1999, across the Hardscrabble mini basin. So on the southern end of the cross section, we have the Gypsum Creek salt wall. So we have evaporite up at the surface and what we think is this extensive thickness of salt. We then have the edge of the mini basin, and I'll show you some detailed work that Savannah did along this edge of the mini basin, the southern edge, where we have characteristic halokinetic folding up against the flank of the salt. You can see how we come into the mini basin itself. The maroon doesn't show a huge amount of thickness variation, but within the Hardscrabble mini basin, we have this huge thickness up to 1,500 meters of the State Bridge, far thicker than anywhere else across the basin. And again, we interpret that because we have a significant phase of subsidence during salt evacuation, during deposition of the State Bridge formation in the Hardscrabble mini basin. And then we come over to the northern side, we have, again, this extensive area of Eagle Valley evaporite cropping out up at the surface, which you see as you drive down I-70 through Eagle and Gypsum. So two salt walls then with this large mini basin sitting between them. So Savannah's thesis area, and again, she completed a thesis in 2021, covers this region of the Eagle Basin. So I'm going to show you a couple of regional sections, and then we'll look at some of the details on the southern side of the Hardscrabble mini basin, which are key in terms of Savannah's interpretations. So here's a regional section. So this is Savannah's map down in the bottom left-hand corner. Again, so it's built from published data, but in this case, we only had USGS and CGS maps published through the northern part of the sector. Basically, this area around Hardscrabble is not published in detail in any quadrangle maps, so we had to collect quite a lot of data to put this together, and that's Savannah's work primarily. But the regional section that Savannah's put together goes C to C prime, basically starts in the south on a salt wall structure, basically just separating the Red Table Mountain mini basin and the Woody Creek mini basin. This is up around Rudye Reservoir. And then the section's going to run across Hardscrabble mini basin, Bellyache mini basin, and then Walcott mini basins to the north. So here's Savannah's one-to-one cross section. So we have the Gyp Hill diaper, which again is close to Rudye Reservoir. We come then to the north through the Red Table Mountain mini basin, very large thickness of maroon, and we're also now picking up a large thickness of the underlying Eagle Valley formation in purple. So as we move into the northern and western parts of the basin, the Eagle Valley formation becomes significantly thicker, and that's sitting between the Eagle Valley evaporite and the maroon. So it's the unit in dark purple in here. So interpreted that this mini basin is welded out, there's no longer any salt at the base of this. We then cross the Gypsum Creek salt wall and come over into the Hardscrabble mini basin. So here's this extensive 1,500 meter thickness of State Bridge formation in the center of the mini basin. You can see that the maroon in this cross section doesn't change thickness very much at all, and we have that information from sections that Savannah's logged. And then the Eagle Valley at the basin here, which we'll focus on in a bit of detail. We then have the Bellyache mini basin with this salt structure sitting in between that to the north. And then we come across the Eagle River salt wall and then into the Walcott mini basin, but we're looking at more of a strike view into that Walcott mini basin. So let's focus then on the work that Savannah did along the southern flank of the Hardscrabble mini basin, because this is really key in terms of our understanding of when this salt wall structure, the Gypsum Creek saltwater, wall started to grow and when the mini basin started to develop. So in particular, I'm going to show you some of the key observations and interpretations of these halokinetic sequences developed in the Eagle Valley Formation, just a few hundred meters at the most from the edge of the salt wall structure. So in the bottom left is a photograph basically looking along strike. So south is off towards the right, north is to the left. So if you come onto the map, we're standing basically in a location approximately here and taking a photograph along strike looking towards the southeast. So the edge of the Gypsum Creek salt wall, I'm just outlining that now with the cursor. And what we're going to focus on is what we see within the Eagle Valley in the purple unit, and then the maroon in the pale blue. So we've changed in terms of the age relationships from what we were seeing in the Aspen area. So within the Eagle Valley Formation, again, we can trace the edge of the salt wall through here. So we're just less than 200 meters probably from the edge of the salt wall. We have beds that are initially right way up, dipping to the north, which are folded round the hinge of a fold and then end up being overturned and dipping to the south. And critically, what Savannah was able to map out is if you come up into the overlying maroon, we have beds dipping gently towards the north at 27 to 30 degrees. So again, we have one of these very high angle truncations, but the unconformity is between the Eagle Valley Formation and the maroon, so significantly older than what we were seeing in the Aspen area. I'll show you a photograph. Here's Savannah out in the field again on a characteristic steep slope in the Eagle Basin, but we have beds in here which are demonstrably right way up. We can see that from a number of different sedimentary structures. We can trace out this contact, and very abruptly at this fold hinge, they turn, upturn, and become overturned at 85 degrees to the south. And again, this is just within a few hundred meters of the salt wall. So we describe this again to that halokinetic drape folding mechanism. Again, here's an example from Giles and Rowan, basically from 2021, where the idea would be that, again, we're seeing this halokinetic drape folding, which develops as we come off the roof of the salt diaper and into the mini basin. Again, I need to stress that this isn't the result of the diaper forcing its way upwards through the sediment. The sediments are drape folding because they're moving down and subsiding down into the mini basin. So they have to drape fold to accommodate that subsidence. So we're looking at fold structures which were developing very early in the development of the Eagle Basin associated with this passive diaperism. Okay, so finally, let me show you what Hayley Thorson's been working on. So Hayley is a current student at Mines, and she's working in this western part of the Eagle Basin. So as we go basically west of Glenwood Springs, we have this relatively thin sliver of evaporites which locally crop out along this southwest edge of the White River uplift. So it's a pretty narrow belt, but we've been finding some very interesting structures in here as well. So this is a map from Scott et al. 2002. So the GSA special publication, which focused on the evaporite structures in the Eagle Basin, primarily looking at their impact in terms of their modern day or recent dissolution and collapse. But they produced this really helpful map along the edge of the Grand Hogback. So I'm just tracing out the Grand Hogback monocline, which again, you'll all be familiar with if you've driven across that west of Glenwood Springs. The evaporites crop out in the black in here. So this is Eagle Valley evaporite. So you can see there's an area over here, basically just north of Newcastle. We then come over to what's called the East Elk Creek diaper in here we've been looking at. We have outcrops of evaporite at Rifle Falls, and then also a pier on Middle Rifle Creek. And there are cross sections that Scott et al. Put together, and we're using those cross sections and can be redrawing and reinterpreting those, considering what we think is this early phase of salt tectonics. So I've just laid out these cross sections. This would be A to A prime, so we're towards the east. And then this is D to D prime, so further over towards the west. And again, if you look in detail, you can see that clearly what Scott et al. Are showing in here is we have evaporite down at what we call the autochthonous level. So this is where it was deposited on top of the Belden. As we come over on the cross-section A to A prime, you can clearly see it becomes diapiric and is now basically affecting not only the Eagle Valley Formation, but the Maroon Formation as well. We shift along strike, and you can see those geometries change somewhat on each of these cross sections. So we're seeing quite a complex array of salt structures. And again, I apologize, I think Haley's in the audience. This is literally from hot off the press. This is a diagram I drew over the weekend from what we were looking at on Friday out in the field. So this is on the Pumapaw Ranch, so that westernmost cross section. And it seems that the geometry is actually even more complicated than we thought. We think this is the first example that we found in 4 years of what appears to be an allochthonous salt sheet. So let me try and explain that. We're actually sitting where this photograph is taken on Eagle Valley evaporite. That runs across the valley, and this becomes a sub-vertical feeder. It's got maroon sitting over on this side, and we go from upper maroon to lower maroon, from right way up, dipping at 85 degrees, to overturned at 60 degrees. We can trace it up this ridge line, and again, we mapped it out along this ridge, and then we go back into the more distant ridge line, and the feeder seems to come up and then turn and become sub-parallel to the Eagle Valley sediments in here. But the issue is, of course, the Eagle Valley sediments are younger than the evaporite depositionally, so this is climbing up section and then running across these folded Eagle Valley beds, and they're basically folded from being right way up to overturned. This salt sheet then sits as an isolated sheet on top of this hill. So we're still trying to get to grips with this, and obviously Haley will be working on this through the rest of her thesis here at Mines, and we'll be putting together detailed cross sections through these areas and restoring them. So let me just summarize them with some questions that we still have and what we're planning to do in the future. We're still not clear on what the basement controls on the salt wall orientation and spacing are in the Eagle Basin. It seems to be more complex than the northwest to southeast trend in the Paradox Basin, but some of that could be the Laramide overprint. We have this hypothesis of the southwest to northeast directed younging of the mini basin fill, but we're concerned that that's an oversimplification. And if it is, how do the mini basins fill through time in 3D, and what were the controls on this? We're still trying to develop some correlative surfaces between the mini basins, and potentially the Aeolian sandstone units may be the best bet we have with that. And then, as I've just shown you, in this western extension of the Eagle Evaporite Basin, it seems to contain some quite different salt structures than we've seen previously, with potentially these allochthonous salt sheets. And we're also seeing collapsed diapers infilled with thick conglomerates. And that's what's kind of behind me in here. This is looking into the area of Bear Wallow Ranch. And this area just between the elk horns is actually a thick, approximately 400-meter thick coarse conglomerate, which is sitting on top of a collapsed salt diaper. And again, we're still working on the details of that. So there will be a lot more to follow in the future. I'd just like to say thanks for everyone again for spending some time listening to me today, and I'll be happy to try and answer questions.
Thank you, Bruce. That was very, very interesting. There's also a lot of questions on this, so I'll kick it right into the question session here. Starting at the top, how do the extensive Paleozoic evaporites in the South Park and Denver Basin relate to the Eagle Basin?
I think they are linked. So I think the Eagle Basin, in terms of the evaporite facies, extended across the what's now the Saguache uplift. I don't believe there was a Saguache uplift there during the late Paleozoic. So I think the western part of South Park, and even extending down to south of Salida, may actually be the southeast termination of the Eagle Basin. So I would expect, and I actually do suspect, there are similar salt structures within the western part of South Park.
Another question was, what role do the thousands of meters of collapse from dissolution in the Carbondale area play in your model, as documented by the Colorado Geologic Society and the USGS in the early 2000s?
So I think that's important, because it, again, is we have to be clear that we're not confusing late stage collapse structures with what we would interpret as being much earlier structures related to salt diapism. So, for instance, the conglomerate I mentioned, there's been some debate as to whether that conglomerate is old, as in late Paleozoic in age, which would mean it would be associated with the passive salt diapism I'm talking about, or it's much, much younger than that, possibly Neogene in age, so it would be related to the collapse. So yes, it's really important that we separate those two phases as clearly as we can. But there are some structures where it's a little difficult to tell whether we might be dealing with late stage collapse or that early phase of passive salt diapism. So that's certainly a very important point. I've lost you, Pete. I think you're muted.
Somehow I got muted. Do you hear me now?
Yep.
Somehow. I don't know how I got muted. Paul Weimer's here has got a long question for you. Dick Devato and Ted Walker did some menial work on the pan-permo stratigraphy of the Eagle Basin in the 1960s and 70s. Both independently recognized the possible basement height in the middle of the central Colorado Trough based on paleocurrents that likely contributed sediments to the area. They interpreted the feature did not have the same relief as the bounding uncomposite and front range highs. Did your group see any evidence for this paleo high that affected the original salt distribution and the evolution of structures?
We don't. And again, this is where it gets interpretive on our end in terms of, yes, I understand and I'm familiar with the work in terms of those paleocurrents. My understanding is, though, that that's really the only evidence for having a basement chord high in the central part of the basin at that time. I would suggest, as an alternative, that those paleocurrents could equally be related to salt structures that developed at that time during that part of the Eagle Basin. Of course, the problem for me is that those salt structures have now been eroded away. So I have no direct evidence to say that they were there, but to me, to base that kind of Sawatch uplift in the Eagle Basin time during the late Paleozoic only on the paleocurrents seems somewhat tenuous to me.
One last question here. What is the data that supports the absence of the Sawatch uplift during the Paleozoic?
So again, I'm kind of re-emphasizing I don't have any data because if the salt wall structures were there, they're now eroded off the crest of the modern Sawatch uplift. Again, I would point to the fact that I strongly believe there are salt-related structures in the western part of South Park and then extending to the south of Salida. So I think there's pretty good evidence. And again, if you look at the isopachs for either the Maroon Formation or indeed for the evaporite itself, they clearly get terminated very abruptly at the more recent Sawatch uplift. So to me, it seems to make reasonable sense to extrapolate the Eagle Basin across the more recent Sawatch uplift and to say that it continued off to the south. Again, I can't prove that the late Paleozoic Sawatch uplift wasn't there because we just don't have the information to say that it must have been salt, but I think it is an alternative hypothesis.
Ron Parker's got a question for you. Any evidence of ground surface extrusion of salt at Namaker, as Don Rasmussen has shown in the paradox?
I'm sorry, can you repeat that one, Pete? I didn't catch it.
Any evidence of ground surface extrusion or extrudation of the salt at Namakers?
Yep.
Don Rasmussen has shown in the paradox.
So that last example I showed from Pumapool with that last slide of that allophthalmos salt sheet, again, an allophthalmos salt sheet is what Don would call a namaker, I think, but that would be salt that would be extruding at between Eagle Valley and Maroon times, so approximately 300 million years ago. So that would be an old structure, but that is the first I'd say, evidence that we have of these Namakea-like structures in the Eagle Basin.
Interesting. Were you or Savannah able to confirm that the state bridge at Hardscrabble Mountain is really 1,500 meters thick?
Yes. It's a short answer. Yeah, we're pretty convinced it is. We know where the top of the maroon is, and we have the Sloan Peak member of the state bridge sitting right at the top of Hardscrabble Mountain. So again, you can maybe quibble slightly with where you want to put the top of the maroon formation, but we would suggest that it gives you at least 1,200 meters of lower state bridge.
There's a question on the seismic slide. I don't know if you want to scroll back to it, and then I can read you the seismic slide question.
Is that on screen still?
I think it was the seismic section at the, yeah, that's the one, right? Yeah. On the seismic section at the front of your presentation, you show what is labeled as a salt sheet on the left.
A salt wall on the left, yeah.
Salt wall, yeah, I see salt wall. Is that salt sheet now in a vertical orientation? I guess that salt wall, is that in a vertical orientation on the left side of the seismic image?
Yes, it is. So
Okay.
this would be, the top of the salt will be up at the surface, and then the base of the salt will be sitting above the Belden Formation at depth.
You had a section at the front end, more at the front, very first one, to demonstrate the size of some of these features.
Oh, you mean the Gulf of Mexico salt? This one?
Yes.
Okay.
So, yeah, that salt sheet on the left side.
Yep. So that's basically, so there's a well basically which must climb up section from the autochthonous salt. It's climbing up section. You can see it's penetrated by the well through here, but then it has a salt diaper. So this would be a salt diaper. I could have labeled that better, growing off the salt sheet.
Gotcha. Thank you.
Welcome.
Well, Bruce, that's it for questions. I think that was an awesome talk. That was really insightful, and I think everybody really, really enjoyed it. We had 90 people here today, and I think that was a really good turnout and a really interesting presentation.
Thanks.
I got a chance to get
Thanks for inviting me. And again, if there are follow-up questions, people can more than happy to take those via email if people want to get in touch and have any. Because again, I just want to emphasize this is very much a work in progress. So we're more than happy to discuss other potential interpretations of what we're seeing at this point.